Hi, and welcome to MAT2008, which is Differential Equations. I hope that you've had a chance to go to the Canvas page for the course and work through the things that I suggested in my initial welcome email. So things like reading the course manual, logging into WebWork, downloading MATLAB, that sort of thing, because we're not really going to talk about course administrative stuff in this lecture. We're actually going to dive straight into why we might actually want to solve differential equations. So we're going to look at two examples which I think will cover basically everything that we're going to be trying to understand in this course. The first one that we're going to have a look at is intracochlear drug delivery, which might seem like, hang on, wait, I thought this was a maths course. But hearing loss is something that actually affects a huge proportion of the world's population, around 5%. And although there are drugs that can help to mitigate some forms of hearing loss, they're very difficult to administer to the region of the ear which needs it. So hearing loss is often caused by little hairs inside the ear, like right within the cochlea, I think. I'm not a biologist, so correct me if I'm wrong. But these little ears get damaged, and you need to somehow deliver the drug right into the ear, so right into this complicated space over here, in order for it to work. And it turns out that because if you were to take medication orally, so take a pill, then that has to get absorbed into the bloodstream, and the bloodstream then has to carry it to the area it needs to go. And it turns out that that doesn't work very well. You don't get enough of the drug, and you don't get it happening lasting long enough to actually have an effect. So one of the things that has been pioneered is this idea of having a very tiny little tube that basically goes right into the ear to the place where the drug needs to be, and over time just gradually puts in a little bit of the drug and at the same time takes out a little bit of fluid. So because our ears are very sensitive, you can't have a buildup of fluid. You need to keep the amount of fluid in the area the same. So this little tube is attached to a pump, and the pump kind of pushes in a bit of drug and pulls out a little bit of fluid. And so over time, you end up with the fluid inside the ear containing the drug that it needs in order to get better. So obviously this is a pretty tricky thing to figure out, and a lot of mathematical models were created in order to understand that. So we're actually going to look at a very, very simple one, just to see how you can take a system like this, where you're trying to solve something like delivering drugs to a part of the body, and model it using a differential equation. So let's see what we've got. So we're going to take a super simple example over here. So we're imagining that the cochlea, which is where we want to deliver our drug to, is just a little container, and it's full of fluid. And although in the way this actually happens in real life, it's a single tube that kind of pushes in fluid and then takes it out, we're going to model this as if we have one pipe going into the cochlea that will deliver the drug, and then we have another pipe going out, which is going to take out the fluid so that we don't get a buildup of fluid. Okay. And now let's try and turn this into a maths problem. So what we want to know is essentially how much drug is there in our cochlea at a particular time. And then if we can model that, we can figure out what parameters, like what is the rate that we need to feed the fluid in, and what concentration of the drug, stuff like that. So we need a mathematical model. So since the thing that we're particularly interested in is how much of the drug is in the cochlea, let us let our variable u of t be the amount in milligrams of the drug that's in the cochlea. So we're imagining that what we want to find out is, how many milligrams of drug at a given time is in the cochlea. We're going to call that thing u of t. Okay, what are the other things that we have to work with? Well, we are going to be pumping fluid in, so we need to know the rate at which our fluid enters and exits our cochlea. So we're going to assume that it enters and exits at the same speed so that it doesn't build up or drain the cochlea. So I'm going to call that R. So that's going to be the rate at which the fluid enters. And since we're dealing with really small amounts here, it wouldn't make sense to use liters, so we're going to use microliters per minute. Okay, so it's a super small amount that's going in and coming out, and gradually you build up the right concentration. Okay, and then the next thing we want to think about is we're pushing fluid into the cochlea. how much of the drug is going to be in the fluid. Obviously, the drug isn't going to be complete. The fluid isn't going to be completely drug. It's going to have some carrier liquid that the drug is in. So we need to think about the concentration of the fluid going in, and that's going to be measured in micrograms per microliter. Okay. And then finally, we're going to need to make some assumptions about the volume of our cochlea. So let's just call that phi. And again, we're going to measure that in microliters, because in liters it would just be silly. So the question that we want to be able to answer is, at a particular time t, how much drug is there in the cochlea? We know that initially there won't be any of the drug, and hopefully over time, as we start administering it, the amount will go up. Then we'll hopefully reach a nice plateau, because we don't want it to keep going up to infinity. And then maybe at some point we want to stop introducing the drug into the cochlea, and then the amount should go down. So that's kind of what we'd like to model. For the moment, we're just going to think about modeling from no drug to, well, hopefully this plateau. How could we do that? Well, let's think about the system. So let's think about what happens in our cochlea over a small time period, a small delta t. Well, we know that if we think about the average change in the amount of drug over delta t, so we write that down, so the average okay, so we're thinking about what is the, over little delta t, how does the amount of drug in the cochlea change? Well, what is causing the change in the amount of drug? If there was no fluid being put in or taken out, then the drug amount wouldn't be changing. So what's causing the change must be, firstly, how much is being put in, and secondly, how much is being taken out. And since we're kind of assuming that the drug doesn't get absorbed or anything like that, so a very simple system here, there's no other way that the drug can leave except when it's leaving through the little pipe, we must have a situation where our total change in the drug amount over delta t must be based on how much goes in less how much goes out. So we're going to have that our average change going in over delta t, so that's our average change going in, not in here, different in, and subtracting off the average change out over delta t. So this is really a kind of, you've probably seen things like this all over the place. This is a conservation law, which basically says if you're not creating something or destroying it, then any system that is kind of, that you're measuring, what goes in less what goes out tells you the total change in that system. You've seen this before if you've done any physics. All right, so this is talking about average change over a small delta t, but as you're probably guessing by the fact that I used a delta t over here, we're going to think about what happens as we make delta t really small. So we make delta t infinitesimal, so we're making our delta t tend to 0, and then what happens? Well, then what we end up with is we have du by dt. So our average change, you'll recall from calculus 1, over delta t as delta t goes to 0 actually gives us our du by dt, our instantaneous rate of change. So this says our instantaneous rate of change and what is that going to be? Well, that's going to be equal to our instantaneous rate in minus our instantaneous rate out. I lost some letters there. Instantaneous, there we go. Okay. So now we need to find formulae for our instantaneous rate in and our instantaneous rate out. So we've got du by dt. Well, what's our instantaneous rate in? If we think about that, we've got some things that we're using here, we know that R is the rate at which the fluid enters. What we're interested in is the instantaneous rate that the drug enters. So we need to think about how much of the drug is entering with a rate of R. And we know that our drug concentration is C1 in the fluid as it's entering. So if we multiply those two together, that will give us the instantaneous rate of change of the drug. So let's just write that down. So that's R times C1. So let's just think about this. So this is rate of fluid, and that's our drug concentration. So together that tells us how much of the drug is entering per unit of time, per minute in this case. All right, so that was pretty straightforward. And now let's think about our instantaneous rate out. How's that going to work? Well, now we need to think about kind of the same idea. We're going to have the same rate going out because we've said we're putting in the same amount of fluid and taking out the same amount of fluid so that we don't get a build-up. So our rate is going to be the same. So that's the rate of fluid in, and in this case, the same thing over here. We've got rate of fluid out. But now we need to think about how much of the drug is leaving, and so we need to know the concentration of the drug within the cochlea. Well, how much is there? Well, so what's the concentration? Well, it's going to be however much drug there is, which is the thing we're actually trying to find, divided by the volume, and that will give us the concentration. So for each of the terms on the right-hand side here, we've got a rate multiplied by a concentration. So for the first term, it's the drug concentration in the fluid going in, and the second term over here, this is drug concentration in the cochlea. So you're probably saying, well, we're making a lot of assumptions here, and we certainly are. So we're assuming that as the drug goes into the cochlea, it gets kind of perfectly mixed. So it's not like there's some diffusion gradient or something over there. And you can start with a simple system like this and then build in complications. But for the moment, this is pretty good. So here we go. We've just created our first differential equation. One of the first things that I would recommend that you do when you're doing something like this is a quick dimensional analysis. What do I mean? Just check that your units make sense. So we're going to check that the units that we have in each term are the same, because otherwise something's gone wrong. So let's think about our units here. So if we look at du by dt, we know that u is measured in micrograms, and we're measuring t in minutes. So overall, the left-hand side here is in micrograms per minute. Okay, so we're really hoping that both of these terms are also in micrograms per minute. Well, let's have a look. So our rate of fluid in, we know, was in microliters per minute. That was this bit. And we know that our drug concentration of the fluid going in was in milligrams per microliter. So if we have a quick check, those will cancel, and this term is looking good because we've got micrograms per minute, which is the same as there. And if we check over here, we should have the same thing. So again, we've got our rate, which is microliters per minute. Look at this term over here. So our U is measured in micrograms, and our volume is in microliters. So again, we get a nice cancelling, and it works. Okay, so this is a kind of quick and dirty way of checking, if you put together a differential equation, that you at least have things of the right type in each of the terms. Obviously, there are many more checks that you can do, but this kind of tells you, well, at least you're not doing anything completely insane. All right, so what do we end up with? Finally, just so that we can see it clearly, we have that the rate of change of the amount of blood, the amount of the drug in our cochlea, the instantaneous rate of change is equal to the rate at which the drug is being administered times the concentration of the drug minus the rate at which it's being administered and leaving times the concentration of the drug in the cochlea. Okay, and that's as far as we're going to go right now. But remember, what we want to do is answer the question, what is u of t? What is that function? If I tell you time 5, then can you tell me what the concentration or what the amount of drug is at time 5? So our goal in this course is basically to be able to take this equation and turn it into the formula for a function. And we will actually learn how to do that later today, just not right now. Okay, so the first part of this course is going to be around techniques for solving this sort of equation, because you probably didn't encounter very many if you did it at all in Calculus 1, but there are lots of techniques. It's kind of like integration, only more so. So that's the first part of this course. But there are plenty of things that you can't model with a single differential equation. So, for example, snowshoe hares and Canadian lynx. These are kind of, it's a canonical example that you will encounter in any differential equation course. So basically, in Canada, it was noticed that Canadian lynx, which preys almost exclusively on snowshoe hares if it can, so they form quite a tightly coupled predator-prey system, and there was lots of data taken. Here it's only from 1980, but there's data going way back to like the 1800s, and it was noticed that the populations kind of follow each other in this cyclical pattern. So if we look at this over here, so our snowshoe hares are the red, so you'll see that they've got a kind of periodic pattern happening there, and then our lynx, which is in blue, is kind of following that. So they don't have their peaks at the same time, but it seems like the two populations are linked together, which makes sense since they kind of the snowshoe hares get eaten by the lynx, and then obviously there are not enough snowshoe hares, so then the lynx die out, and then because there are not enough predators, the snowshoe hares population booms. So it kind of makes sense, but it would be nice to be able to model that in some sort of useful way. So let's try and put that together. Well, let's think about how we can do that. So we are going to call our population of hares h of t. So that's what we'd like to know. How do we describe the population of our hares over time? So this would be measured in number of hares, and we're going to not be very innovative here. We're just going to call our population of lynx L of t. And here we're measuring t time in years. So let's make some assumptions and see what we can get out of here. So if there are no lynx present, then we need to make some assumption about how the hares reproduce. And a fairly standard one for things like hares is to assume that they produce at a rate proportional to their current population, and they don't get affected by overcrowding. So we're assuming that it's Canada, there's a lot of space. If there are no predators, then the hares just keep multiplying and multiplying based on how many they are, which kind of makes sense. You have more hares, then you have more breeding females, so the rate at which they produce overall is going to increase. Okay, so can we write down an equation which says that? Well, we're talking about the rate at which the hares, the rate at which they reproduce is proportional to their population. What does that say? Well, that says the rate, so that's dH by dt, is proportional to the population, so that's proportional to h. Can we turn that into an equation? Well, yes, we can. Being proportional says that dH by dt must be equal to some constant, which we're just going to call a here, times by the population. Okay, so that's assuming that there are no lynx. So we know that we need to have a term that looks something like that, but it's probably going to be modified if there are lynx. Okay, so now let's think about the rate at which hares are consumed by the lynx. So suppose now we've got a system where we have both of them. So now our poor little hares, our bunnies, are not just being free to reproduce ad infinitum. Some of them get eaten. Can we model that? So let's add in that term. So we know that we've got a term which comes from the reproduction of our hares, but we're going to subtract off some hares based on the predation by the lynxes. And if we think about how we might model that, Well, in order to kind of have a hare get eaten by a lynx, they need to interact. So it's going to depend on both how many hares there are and how many lynx. If there are not very many lynxes, then there should be a small term because there won't be a lot of interactions resulting in an eaten bunny. On the other hand, if there are a huge number of lynxes and a very small number of bunnies, again, not going to be a big term because there won't be a lot of bunnies to get eaten. So it seems like probably having a term which multiplies these two together will capture the fact that we need to have an interaction for a bunny to get eaten. And as per usual, we're going to put in a constant, which you could hopefully determine by getting actual data. So let's see. So if we're thinking about our bunnies, our hares, what have we got? Well, the rate of change of the population of bunnies is determined by the bunnies going into the population, which is given by this term over here, less the bunnies going out of the system, which here we're just assuming is the ones that get eaten. Okay, so we haven't here included bunnies that die of natural causes. We're assuming that the natural cause here is being eaten by a lynx. Okay, so this gives us an equation that models our bunny population. Let's do the same trick for our lynxes. So let's think about a simple situation where there are no bunnies. So just like we started simply up here with no lynx, now we've got no bunnies. What's happening to our lynx population? Well, we're going to keep it super simple and assume that there's nothing else that the lynx could eat. So if there are no bunnies, then the lynx are going to die out because they have nothing to eat. And the number who die is going to depend on how many are still alive. So again, we have a situation where our population is going to be dependent on itself, or the rate of change of the population is going to depend on the actual population. We're going to need a constant. But here it's going to be a negative term because these are lynx that are dying. They're leaving the population. Okay, good so far. And now we need to think a little bit more. Now suppose we have bunnies in there. What is this going to do to the lynx population? So our lynx receive a benefit from the hare population. The rate at which a lynx is born, so we can think about the fact that the lynx gets to eat bunnies and survive and reproduce results in more lynxes. So we're going to have the rate at which our lynx is born is proportional to the number of hares that are eaten, because that's kind of we're thinking of that as a kind of a proxy for a healthy lynx population. And the number of hares that are eaten, we've already seen over here, is going to be proportional to the number of interactions that we have between hare and lynx. So we're going to have a term that looks like this, another interaction term, and just a constant to modify that. So again, we have a kind of conservation thing going on here. The rate of change of our lynx population is given by the lynxes leaving the population, plus the lynxes adding into the population. So you'll find that this comes up a lot in modeling, thinking about things in terms of conservation law. All right, so we've got another equation over here. But the important thing you'll notice is that this equation here, which is telling us about the hare population, includes our equation, our formula for the lynx population. And similarly, if we have a look at our differential equation that models the lynx population, it requires that we know what the hare population is. So we have what's called two coupled differential equations. We can't solve one without the other. So we have a system of differential equations, and basically the second part of this course is how do you solve systems. So if you have two or more differential equations that are linked like this, we need some techniques. Oops, that should be an A. So you can think about it, you've seen things similar to this before. You've seen two equations and two unknowns. Well, here we have two equations and two unknowns. It's just that they happen to be two differential equations. So the solution isn't quite as simple as you've seen before for solving two equations and two unknowns, but there are techniques. So this gives us a whole kind of, the second part of the course will be around systems like this. All right, so this gives you an overview of why we might want to solve differential equations. We've seen two very different examples, something from drug delivery in the ear to kind of an eco problem. I haven't included any of the many physics equations that are all differential equations because I'm sure you're kind of familiar with them. But hopefully this gives you a reason to be doing this course. Differential equations, they just happen everywhere. So what we're going to do now briefly is just do a little talk about terminology. So I've actually finished this bit, and then I'm going to take a break and look at two techniques for solving a particular kind of differential equation. So just to expand a little bit on what I was saying. So this week we're talking about first order equations, which we'll come to the terminology in a moment, and possibly a little bit about numerical methods. For the 2 weeks after, we'll be talking about second order equations, which you'll know more about in a little bit. And then we're going to learn something called the Laplace transform, which I'm not going to say any more about right now because it won't make a lot of sense. But basically, all of this is talking about single equations, single differential equations, like the Cochlear example that we saw. And then week 5 and 6, we're going to be using what we learned in the Laplace transform in order to be able to solve problems like the predator-prey one that we saw. So that's our goal. All right, so just some terminology. So you might have heard the term ordinary differential equations applied to this course. And usually if someone just talks about a differential equation, they're probably meaning an ordinary differential equation. What does this mean? Well, it's distinct from partial differential equations. So an ordinary differential equation is an equation, so something equals something else, in which we have a function of a single independent variable, t. And the equation includes derivatives of that function. So, for example, over here, here's an ordinary differential equation on u. So our unknown function u is just a function of the variable t. No other functions, no other variables. And we have an equation that includes a derivative of u. Now, it can happen that we can have some other function of a single variable as well. So this gives us a system of differential equations, but there's still ordinary differential equations because the derivatives that we have in here are ordinary derivatives of a function of just one variable. On the other hand, and this probably will help you see the difference, you might have a function, for example, u, which is a function of, for example, x and t. So these are the kinds of things, if you took multivariate calculus with me last period, that we encountered. Now we know that you can take partial derivatives of functions of more than one variable, and in that case, you can use those different partial derivatives to put together equations. So for example, over here we have the wave equation, which you might have seen in physics. So it is an equation, it has differentials in it, but the key thing is they are partial differentials. So here's the second derivative of u with respect to t, and here's the second derivative of u with respect to x. And you can actually have systems of partial derivatives, partial differential equations, just like we had systems of ODEs here. You will often hear people just talk about ODEs, ordinary differential equations, and PDEs. We are not going to look at any PDEs in this course. That's the subject of a different course. We're looking at ordinary differential equations, either single ones, just living their lives by themselves, or coupled ones, which we'll look at in the second part of the course. There are there's quite a lot of terminology here, but it will get very familiar. So one of the ways of classifying a differential equation is what is the highest derivative that you have. So far we've only seen really first order differential equations. So here we've got the first derivative of u, here we've got the first derivative of v, but there's no reason you couldn't have higher order derivatives. So one way of identifying a differential equation is by the highest order derivative. So for example, if I had this, then this would be a third order differential equation because the highest partial derivative, the highest ordinary derivative is 3. Okay, so talking about the order is kind of the first thing that you'll talk about. This used to be a lot more important before computer systems that could solve differential equations numerically or analytically, because how you solved it depended on the order. So that was the first thing that you kind of needed to know. Nowadays it's kind of like, well, it's a differential equation, you put it into MATLAB, it's probably going to solve it, and you don't have to think about it quite as much, but you still kind of need to know sometimes. Another thing that we can think about is the form of the ordinary differential equation. So the next way that we differentiate them, and this is hugely to do with how one solves them, is whether they're linear or not. So you know that something is linear if it looks, well, let's keep it simple, something like this is a linear graph. So y is a linear function of x. It's proportional to x with some constant. What does that mean if you're going to be a linear ODE? Well, remember our original unknown function is u of t, and if you look at all the terms that we've got in this equation over here, our u and its derivatives only ever appear as themselves. No powers, no roots, nothing like that. It's just u or du or whatever, and we're multiplying them by something. So we might multiply each term by itself, by something, and then we add it to other terms. So we don't have any situations, if you're a linear DE, where you might have, for example, the second derivative, at times by the first derivative. So there are no cross terms, there are no powers of terms, nothing like that. In each term that we have in a linear differential equation, we just have one derivative of our original unknown function multiplied by something. That's it. And finally, on this, we might have one, which we think of, it might not be the constant term, but it's the term that doesn't have anything to do with u of t, which is kind of acting like this c over here. So it might change over time, but it's not dependent on u. Okay. If you have a differential equation that doesn't look like that, then it's nonlinear. That's as good as it gets. So we've got lots of other important adjectives that we'll learn as we go along. So you will learn about constant coefficient. No surprises here. It's when these coefficients over here don't depend on time, they're constant. Autonomous we'll learn probably later today. Separable we'll definitely learn later today. Homogeneous and more. But it makes sense to learn them as we go along. So what I would recommend for this course is that you start making yourself kind of a little dictionary and just, all the vocab, because it is relevant and it gets used wherever differential equations are. So knowing about it is important. Okay. So we're going to start at the beginning, first order equations. So remember, first order means that the highest derivative that we have is a first derivative. So we're looking at things of the form du by dt is equal to some function of probably u and t. Okay, so that's the most general form, but we'll come back to that general form. The first thing I want to point out is that you've actually been solving first order differential equations for quite a while. For example, we could say find a general solution to the ordinary differential equation, this thingy over here. You probably didn't realize when you were solving this in calculus that this was an ordinary differential equation, but it totally is. Maybe rewriting it as du by dt is equal to 3t squared. What is this saying? This is saying, please find me the function u whose derivative is 3t squared. So we take the antiderivative and off we go. If we were writing this out formally, what you'd be doing is you'd saying, well, I'm going to integrate with respect to t. We know that, thanks to the fundamental theorem of calculus, the integral of the derivative is just going to give us u of t, so that's delightful. What is the antiderivative of 3t squared? I hope that you immediately write down t3 plus c, and we're done. So we just solved our first ordinary differential equation. I wish that, this was as far as we had to go and we could all just go and have coffee for the rest of the term, but we can't, because what happens is usually we don't have a simple situation where our function, so the one that we just seen, looks like this. Our derivative only depended on t. It didn't have any u's in it. But usually that doesn't happen. So usually we're going to have that our derivative is equal to some function that includes t's and u's. And then we can't just straight antidifferentiate. And it gets a little bit worse than that. There's no single technique that will solve every problem. It depends very much on the structure of the differential equation. So what we're going to have a look at is two kinds of first orders that we can solve, linear and separable. But for now, take a break, go and get some coffee, and then maybe come back and we will tackle these two techniques.